called 倚天屠龙记, right? And then the story has got a young boy learning Kung Fu from a master, right? So, and the young boy's name is Zhang Wuji, right? He learned from the Kung Fu master. And the Kung Fu master taught him the Kung Fu, right? He must remember all this, right? So he remembers that, then he went and practice. And 1 week later, the master asked him, have you been practicing? Do you still remember what I taught you? Then he said, yes, I remember 100% what you taught me. Okay? Then he said, okay, go and practice again. Then a month later, the master asked him again, have you been practicing and do you still remember what I taught you? He said, I have been practicing, but I've forgotten 50% of what you taught me. Right? Then the master said, you go practice again. And until 2 months later, the master asked him again. He said, yes, I have been practicing, but I have forgotten what you have taught me. The master said, good, you pass, right? You pass, right? So the moral of the story is this. The moral of the story is this. When you learn something, when it becomes part of you, then it's really you, understand? Yeah, if you still need to remember, this is the formula, that is the formula, this is what I say, what the lecturer say, and it's not part of you yet. Right? You have to internalize it. You have to internalize it until it becomes part of you when you go and think through things. Okay? So to do well in this course, the final exam is open book, right? So I test you on the concept. So to do well in this course, you have to forget what I taught you. Understand? Okay? You have to forget what I taught you. Now, to do that, a lot of time, it's about thinking through and about what you learn. In fact, the best way to prepare for the exam for this course is actually to give yourself a lecture without looking at the slides. Without looking at the slides, give yourself a lecture. If you can give yourself a lecture to explain to yourself the entire course content, I think you'll do very well in the final exam, alright? Right? So to prepare for this final exam, give yourself a lecture. Okay, so coming back to this, we went through the derivation of how to compute the beam size, right? And this is very important because when you do frequency analysis, when you do FFT, you dump the signal in and then the FFT will give you another array of numbers. You must know how to interpret them, right? You must know how to interpret them. So the first number returned by an FFT library is 0, okay? 0 frequency, that means an offset, there's no vibration, 0 frequency. Okay, and then it gives you the first frequency, second frequency, third frequency, right? And then on this side you have minus F1, minus F2, minus F3, minus F4. Okay, so they always give it to you this way. In fact, all FFT libraries that I've come across all give you this way. But sometimes it's okay to, when you want to perform some operation, it's okay to stay here, stay this way. But sometimes human beings like to see something symmetrical, right? You want to see 0 in the middle and then plus, minus on both sides. So in order to do that, you can do something called FFT shift, right? The library will give you FFT shift, and that will actually bring the 0 to the middle. Am I losing you? Am I losing you? Very good. Now, remember what I said just now. The moment you use FFT, everything is periodic. Everything is periodic, right? So the FFT library gives you this output. It doesn't mean that outside is 0. Outside means this whole thing repeats again, understand? Okay? So this whole thing repeats again, that means it's 0, F1, F2, F3, right? Right? So when you do FFT shift, what you are asking for is, instead of giving me this chunk, can you give me this chunk instead with 0 in the middle? Understand? Understand? Then I have positive on the right hand side, negative on the on the left hand side. It's more intuitive for me. Is that okay, everyone? Is it okay? Okay. So, and then to answer how many hertz for the bin size, right? We need to understand the concept of frequency binning, and this is a bunch of derivations. Not exactly derivations, but it's like trying to change from continuous variable to discrete variable, and change up to a certain point in time. You can actually do the comparison between the DFT formula and what we have there, and then conclude the relationship between the bin size and the actual hertz. Okay, let me quickly go through this. Right. So the very first equation is the continuous time Fourier transform, right? Yeah? Continuous time Fourier transform of the function h, right? Right? And then if you change the dt into delta t, you change the dt into delta t, then the time must be equal to n steps of delta t, right? Delta t is the step. Delta t is the step here, right? So this is n0, n1, n2, n3, right? And n3 is equivalent to how many seconds? 3 times the gap here, which is delta t. Understand? Is that okay? Right. And so delta t being constant, you bring it out, and then you get this function. And delta t is actually equal to 1 over fs, right? So this is the sampling interval, right? This is the sampling interval, and sampling frequency is just 1 over the sampling interval. Okay, so for example, if you have 10 of these within 1 second, so your delta t is 0.1 seconds, right? Right? And we have 10 points within 1 second, so sampling frequency is 10 hertz, right? Right? So it's just a 1 over, it's a reciprocal relationship. Okay? And so we can write it here, and then your delta t, you can write it this way also, 1 over fs. So from here to here, no problem, right? Okay, right? And then now, our next step is we also go and discretize the frequency axis. So instead of continuous frequency axis, we are going to change them into delta f also. Steps of delta f, right? So let f equal to k times delta f. Delta f is the frequency bin, right? We also describe the frequency axis using the frequency step, right? So you change the f, you change this f here to here. Okay? And then you compare the two. You compare that, you know that the DFT equations, the discrete Fourier transform equations is this, right? So this must equate to here, right? And you end up with this expression. I'll give you 15 seconds to look through. Everyone okay with here? Until here? Are you all okay? Right? So the delta f is actually equal to sampling frequency divided by n, the capital N. Okay? Is that all right? just now, quite a lot of you came in late. Was it because you came from another class, or was it because of the shuttle bus? Shuttle bus or another class? Shuttle bus or another class?
MRT delay.
Huh?
MRT delay.
MRT delay today. Oh dear. So, yeah. So the next. So the frequency base is equal delta f is equal to ns divided by n, right? And ns is the sampling frequency. That means how many points per second you sample the signal. And n is the number of points sent as input to FFT, right? You get the points and then you send it to FFT. And then you got the delta f. Any questions so far? Okay, so in other words, every time you get an FFT array, right? You see the positions. Let's say the output is a frequency axis, right? And then it's discretized frequency axis. You look at the k, right? K equals 0, 1, 2, 3, 4. Then k equals to 5. You want to see how many hertz is it? You just use 5 times the delta f here, the frequency in here. That's how you use it. Is that alright? You will be doing tutorials on this, and one of the tutorials, not the next one. One of the tutorials I'll require you to say some sinusoidal wave in the air, right? And then you sample and record it, and then you see for yourself that you can actually analyze and know what frequency exactly is it. Okay? Yes?
Delta F is related with F0.
Delta F.
I'm sorry.
No. Delta F is nothing to do with the F0. The F0 we are talking about the fundamental frequency here. Delta F is related to what's the sampling here. Right. So it's potentially confusing again. The sampling frequency is how fast you sample the signal per second. Just now when I say F0, it is the fundamental period of the signal. There are different things. Alright? Okay? Oh, yes.
Is the sampling frequency like sampling the number of points? As in, does this have a limit like higher than like cannot be more than one, for example, because cannot sample more frequently than the number of points there?
No. The signal that you're sampling is continuous curve.
Okay.
So you can sample infinite number of points. Okay? The curve that you are sampling is music in the air, right? The vibrations in the air, they are analog. The whole axis is continuous. So you can sample as many points as you like. Yes?
Does that mean that like since like there's like n frequency bins, does that mean that like the frequencies in the frequency bin will always be less than fs?
Will always be less than?
As the sampling frequency.
Yes, that's a very good observation. That's a very good observation, right? Because if that's a very good observation, right? So the observation is when the sampling frequency fs, right? Does it put a limit to the highest frequency that you can represent? That's what you're asking, right?
Yes.
And the answer is yes, and that's absolutely very important question. Later on when we do the sampling theory, we come to that, right? And that is reasonable, right? Because if my speed is very slow, the frequency is low, right? and you can afford to sample very slowly, right? Right? If my speech is very fast, and then you still sample very slowly, right? You're going to miss certain things, right? Right? Because the frequency that you can represent is limited by the sampling frequency. So if your sampling frequency is too slow, you can only represent certain frequencies up to some low frequency, right? The higher ones you cannot. Yeah. That's the kind of things that I like. That's the kind of questions I like because it shows that you're thinking, right? Thinking. You go through and thinking. And you have to do this and then to internalize the knowledge, so to speak. Okay, any other question? Right, so as I say, if you do FFT, the first item is always 0 frequency, then delta F, 2 delta F, 3 delta F, and then minus delta F, minus 2 delta F, minus 3 delta F, minus 4 delta F. Right? When you have even number, the negative side always has got a more, right? Minus 4 here, you don't have a positive 4 here. Because one space is used up by the 0 already, right? Okay? And then, of course, we know that this whole thing is periodic, so the whole thing repeats here, right? So instead of showing this interval, you could have shown this interval instead, understand? This interval. And this interval, because the whole thing is periodic, then it's actually this part. So it becomes 0 in the middle, and then positive and negative. Is that okay? Okay, but FFT shift is for our own visual consumption. Right? Sometimes you don't need to do that if you're not viewing it. Okay, so for example, if you have a 50 Hertz sine wave, by the way, the sine wave is not any virtual construct. If you play a tuning fork, you know the musical instrument tuning fork, you hit it, it's a pure sinusoidal wave, understand? When you whistle, your whistle, human whistling is also quite sinusoidal. Alright? So it's very single tone, so to speak, one frequency only. Right? So if you have a 50 Hertz sine wave and you do the Fourier transform, right? 50 Hertz, this is 50 Hertz, right? Right? And then you store this 50 Hertz in an array. Then you sample into an array. You sample into an array, and then you do FFT. You don't get this. This is after shifting, okay? For FFT, you get this positive one to happen here. You actually get something like that. FFT output gives you something like that, understand? The positive frequency and the negative frequency. It's only after FFT shift that you get something like that. Right? And the whole thing is because the whole thing here is a periodic signal, and from here onwards it repeats again. So this pink color side actually happens here. So for after FFT shift, all they need to do is to shift the display window to here. To focus on this part. Is that okay? Is that okay? Is that okay? Yes. Yes, yes.
But then, something about that, maybe I'm probably confused, but then, that means you want to decrease the sampling frequency and increase the N as far as possible.
Yeah.
But then, decreasing the sampling frequency doesn't sound right.
So there's a paradox here. I'm glad you asked this question. So the question that Celeste, right? So let's ask is, isn't it good to have frequency beat delta F as small as possible? Then you have more resolution, right? More resolution, right? Right? So delta F small, the smaller the better, right? Right? And how to make delta F small? You use a slower sampling frequency, right? That's something very logical, right? But that's kind of like paradoxical because now you're saying, in order to get very good resolution, you should use very slow sampling, right? Intuitively, it doesn't really make sense, all right? Right? So why is there a paradox? Why is there a problem? Anyone? Come on. Think about it. Yes?
It decreased the max frequency generated.
It decreased the max frequency. Yes, that's one thing. But there's another very glaring answer if you just look at here. So you want delta F to be small, Fs to be small. Fs small is good, right? Right? But when Fs is small, sampling very slowly, do you think you have a big N? Do you think you have a big N, given the same time frame? You just few number of points also, right? So N is also small.
So you can sample for longer.
Sorry?
So you can just sample for longer.
You can sample for longer, yes. You sample for longer. You sample for longer, you have more N. But the scaling is fixed, right? That means how do you compute N? How many points is N? N is actually equal to Fs times your time, right? Right? Time times the sampling rate equal to number of points you have, right? See, delta F is equal to Fs divided by N, right? So what Celeste is saying is delta F is the resolution, the mean size, right? We want this to be small, right? If you want this to be small, then you put Fs to be small. But so Fs to be small means you're sampling very slowly, which is kind of strange, right? Right? But the problem is when you sample very slowly, for the same time interval, your N also reduces. Because N is actually equal to sampling frequency multiplied by time, right? 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 So in other words, delta F is equal to Fs divided by Fs times time. Time is the time interval, right? Is equal to 1 over the time interval, right? And so let's say then we make it very, very long. Right? We make it very, very long. So in other words, if I have a signal, I sample it for a long time, then the frequency gain will be smaller. Right? Okay? And that's a true statement actually. That's a true statement. But the problem is that usually in practice that time interval is not determined by you. It's the duration of the signal. It's the duration of the signal. It's not determined by you. That's number one. Number two, you cannot forever just anyhow reduce the sampling rate. Because as we know, if you use a too slow a sampling rate, you miss the signal also, right? Okay? So in other words, in order to get a small delta F, sure you can decrease Fs, but you cannot anyhow decrease Fs because Fs too slow, you're going to miss the signal, understand? Because signal change very fast, right? You cannot. Okay? let's say, then why not we sample for a longer period of time? But most of the time, the signals given to you is of a fixed interval that you're analyzing. Okay? There are more to it, but for the time being, I think this is sufficient for the time being. Any other question? Any other question? So the part that a lot of people confuse again is also the effect of discretization of time and of frequency axis. Okay? If you are still confused, you just remember this. As long as you discretize one axis, the other domain becomes periodic. Understand? And in the case of discrete Fourier transform, FFT, right, both axes are discretized because you're using computer arrays to represent it, right? So when both axes are discretized, both sides must be periodic. Okay, that's what you need to remember. Okay, so okay, another thing is sometimes we instead of writing 2 pi f, we prefer to write it as omega, right? Omega is equal to 2 pi f. And you know why omega is equal to 2 pi f, right? F is cycles per second. Every cycle is 2 pi, right? So omega radial frequency is 2 pi f. 2 pi f. This slides I don't intend to go through. You just I don't intend to go through, but it's basically to show that it's because of your 2 pi here and everything is in discretized form, right? It's in discretized, so it's integer here. It's integer here, and then you have this kind of periodicity. For those of you maybe doing some other work, I don't know, radar, LiDAR, those kind of work, there's something called phase wrapping, phase unwrapping kind of thing. It refers to this because when you have 0 to 2 pi, and then you have 3 pi, 4 pi and all that, but then because they are periodic, right? 0 to 2 pi, and then here onwards, they still represent as 0 to 2 pi, and they won't represent a higher number. So it's something related here. I think I confused you by saying that, right? Am I confusing you? Am I confusing you? If I confuse you by saying what I just said like 1 minute ago, forget it. It's not that. Just ignore that. It's not so. It's something you know, and it's something you already know. And if you don't understand, it's my fault. I confuse you. Okay. This set of slides just show that when you discretize both axes, time axis and frequency axis, both sets are periodic. Just remember that. Okay, so this is just a summary. This slide is just a summary again, right? The very first time, when you do the continuous time Fourier transform, the top one is continuous time Fourier transform. Right, continuous time Fourier transform, everything is both axes are continuous. Time axis continuous, frequency axis are continuous, right? And then the moment you go and discretize the time, wait. We did not do DTFT. We did not do DTFT in this course. We straight away jump from CTFT to DFT. Write it down. Right? Don't lose sleep over DTFT. The DTFT is the time axis is discretized, but frequency axis is not discretized. Understand? DTFT has got in fact there's a book. Okay, I think one of you asked me for reference book or some reference material, and I think there are many on this topic of Fourier, right? But every time for Fourier kind of analysis, when you see the word Oppenheim, right? Oppenheim, you won't go wrong, right? Oppenheim is a professor in MIT, and he published quite well in signal processing. He read books on it. There's one book written by Oppenheim. It's called Discrete Time Fourier Transform, DTFT, right? But when you look at online materials, you just be aware what kind of Fourier transform people are talking about, okay? And for all intents and purposes, if you don't have time, you just go and study what is DFT. DFT, we just have to, because that's what we do, right? Okay, so discrete time Fourier transform is different because the frequency axis is still continuous, right? And then discrete time axis, discrete frequency axis, we call it discrete Fourier transform, which is the FFT. FFT is a fast implementation of DFT, right? So we will be using this over and over again, right? Okay? Is that okay? Is that okay? And then the same applies to the inverse side. You have the inverse Fourier transform, right? And this is just to illustrate, right? If you have a signal here, right? Signal here, and then when you do continuous time Fourier transform, you assume that the period is infinity, right? You integrate from minus infinity to plus infinity. Can you see the mouse? Right? And then you get this Fourier spectrum, right? And the zero is here, and it's not periodic. It's not periodic because all the axis here is continuous. But the moment you go and do the sampling, the time axis becomes discretized, right? Time axis discretized. In the continuous world, it becomes like that, understand? It becomes periodic. So this is discrete time Fourier transform. Okay? Now if you also go and discretize the frequency axis, then this part here becomes periodic, understand? Because you discretize one axis, the other axis becomes periodic. Okay? So when you have a signal like that, and then you sample it and you do FFT, you end up dealing with a signal like that. Is that clear? Is that clear? Okay, you think you're playing with this signal, but no, you're actually playing with this signal when you do FFT. Okay? Okay? Although when you input the FFT, you only input this one-to-one period, right? But the FFT computation actually treats the signal as a periodic one. They also give you one output like that, right? But the implicit assumption is, implicit meaning is outside also it repeats. Is that okay? So just remember when you do FFT, this is the periodicity constraint. And then, is it okay, everyone? Okay? Now the next thing we want to do is to go and look at some Fourier transform tests. We are going to look at the results that is just enough for our course. Alright? There are many different types of Fourier transform tests. We're just looking at just a few of them. Okay? So it's useful to know a few common Fourier transform results. We need to know the results of Fourier transform of an impulse. An impulse, later on we'll see the slides, right? But an impulse is defined as, you think of impulse as giving someone a punch. You pack a punch and then you punch someone, okay? The impulse. In the definition of impulse says this. says this. It is a time domain, let's say time domain, right? Time. At time 0, you have a spike. You have a spike. And this spike goes to infinity. And the width of this, right? The width of this thing goes to 0, understand? Okay? So impulse is something that goes to infinity, and then the width of it is 0. So you think of it as a rectangle pulse, understand? But this rectangle pulse is extremely thin, extremely tall, understand? Think of it as a rectangular pulse in time domain, a rectangular pulse, and this pulse is extremely tall, extremely thin. Okay? And since there are no maths professor here, I'm going to say this, infinity multiplied by 0 equal to 1. Infinity multiplied by 0 equal to 1. So the area under the curve, so think of it as a very thin kind of rectangular pulse, and this is like infinity, the width here is 0, infinity multiplied by 0 equal to 1. Okay, basically what it's trying to say is the area under the curve is 1, right? That's the definition of impulse. Area under the curve is 1. Right? Area under the curve is 1. So remember that. That's the definition of impulse. And then we have a train of impulses, meaning a few impulses, one after another. And then we have a rectangular function also. Why do we study rectangular function? Rectangular function actually brings us back to reality. Rectangular function brings us back to reality because our mathematical representation is impulse infinite strength and 0 wave, right? Right? But in practice, you're not going to be able to implement that, right? So in practice, it's more like a rectangular function. So it's good to know what exactly is a rectangular functions of Fourier transform. And then the very important ones are the sine and cosine. Just this few only. Okay, just this few only. Alright, now it's 10:52. Let's give ourselves a longer break. Let's say we come back at 11 o'clock. We take a break now, we come back at 11 o'clock and continue. Thank you. sample and you discriminate the actual, not the concentration. It will be this one. I mean, they do two things now. It will be commercial. So you have infinite height, infinitesimally small width, and height times width equal to 1. So infinity times 0 equal to 1. Okay? And then for the discrete time case, it's very straightforward. It's just 0 elsewhere, and then just a 1 here. There is a print here. There shouldn't be 2 dots here. Just 1 dot only. Just 1 dot only. Just a print here. Okay? So that's an impulse. An impulse always sits at 0. Okay? The definition of impulse is it sits at 0. Of course, it can shift impulse to elsewhere. Right? So to represent impulse, you can write this in your notes. To represent impulse, you usually use a delta function. Right? You delta function and you write it this way. Okay, and this is equal to infinity at t equal to 0 and 0 elsewhere. Right? And then in the discrete time case, you write it this way. This is equal to 1 when n is equal to 0, and it's 0 otherwise. Can you see that? Yeah. Okay, so that's the definition for impulse. A delta function. Delta function impulse, right? So impulse will only have value when the argument is 0. Understand? Okay? So if this represents an impulse at time t equal to 0, right? Right? If you have an impulse that sits at time t equal to 5, 0 is here, but impulse is at 5. How would you write the function? How do you write the function? Anyone? Delta? I think someone take the answer. T minus 5. T minus 5. Delta T minus 5. Okay? Because when T equal to 5, the argument inside becomes 0. So you have an impulse, understand? Okay? So the position of impulse is this way. Write it down, write it down. As I say, train to learn how to take notes. So, discrete time impulse function is what I wrote there, right? Okay. Now you can have a train of impulses. A train of impulses is what was shown underneath, right? So you can have train of impulses that are separated by n steps apart. That's what it shows there. Okay, the n steps apart. Okay, so this is called a train of impulses. Train of impulses. Okay, inside, in between is all 0. In between is 0. Okay, in between is 0. Write it down. In between are 0. In between are all 0. Write it down. Because this can be confusing later. So I want you to write it down on your note that in between on the axis here they are all 0s. Okay, so this is a train of impulses. Okay? Okay? Sorry? What's the what? The y-axis? The y-axis is the value of this function. It's a value. That means y equal to delta t. If you let's say you want to talk about physical, right? Physical. I give you a punch, then the y-axis is the strength where I punch you. Yeah. No, y-axis is the value of the impulse. So 0, time equal to 0, nothing, I didn't do anything. Until time equal to 5, I give you a punch. Then 0 again, I don't do anything. Yeah. So look at a few important results for this FFT now. This one is just some illustration of the FFT result. When you input 1, 0, 0, 0, this is an impulse function, right? Impulse at time t equal to 0 is 1, right? Right? And then 0, 0, 0. The A is an impulse function, right? Yes? Right? And then you do an FFT of A, right? FFT of A, you get something like that, right? Which means that an impulse, when you do FFT, you tell you that that impulse comprises all kinds of frequencies at the same strength, okay? There is a term for this, it's called white. Because when sunlight, all kinds of colors, when they mix together, it becomes white, right? So this is one result that you have to remember, right? When you punch someone, right, that punch itself in terms of frequency is all kinds of frequencies are there. Okay? Okay? Any question? Any question? No, I use this FFT, 4 points FFT. 4 points FFT, you know, actually if you don't put the 4 there, they will also take it as 4 points, right? Because you input 4 points, right? Right? Now, listen, this is something that I'm going to tell you now, but we didn't do it just now. All the while, I told you that when you do FFT, you just sample and then you dump it in and you get an FFT result, right? And you sample, the number of points is capital N, right? Capital N, right? Yeah. But when you do FFT, right, sometimes you want to increase your N. That means your signal is like that, right? I sample them, right? I have this capital N here, but sometimes I want to lengthen the array by adding zeros to it. Okay? This is something I haven't taught you yet. I haven't taught you listen up. When you do FFT, you are allowed to add zeros to the back so that your N becomes bigger, understand? Okay? And by adding zero, it's not going to disturb your frequency analysis. Okay? Okay? So, and now, the other way around is if you input a constant vector. A constant vector means there's no oscillation, right? Yeah? Constant means there's no oscillation, right? The signal itself, no oscillation, right? So when you do frequency analysis, of course they'll tell you there's no frequency except a zero frequency component, understand? It's reasonable, right? Okay or not? And if you look at it, if you have input 1, 0, 0, 0, you do Fourier transform with 1, 1, 1, 1. And to get back 1, 0, 0 from 1, 1, 1, 1, you do inverse Fourier transform, right? Right? So 1, 1, 1, 1, you do inverse Fourier transform, you get 1, 0, 0, 0, okay? Right? And because they're so, but this one is, your 1, 1, 1 is in the time domain, and this is in the frequency domain. Okay, but you see the similarity here between forward and inverse Fourier transform. Right? Are you okay? Yes? So let's ask the question. Why is this 4? Why is this not 8? What kind of thing, right? Right? Is when you compute using the Fourier transform equation, it will give you 4. Right? But remember what I say in this course. Loudness does not matter, understand? So whether is it 4 or 3, actually I don't care. In fact, throughout my life using Fourier transform, very, I think it's I think 99.9% of the time I don't even care what exactly is the absolute value here. Understand? The actual value here. It is the shape of this output that matters. Because it's the shape of the output that determines the music and the voice that you listen to, understand? Okay? The 4 or 8 or is just a scale factor. Louder, softer, it doesn't matter. Unless you're very particular about loud and soft, then you're particular about that number. Okay? But if you plug in equations to compute, you get 4. Okay? So this is another very important one, and you have to know it very, very well. The Fourier transform of a cosine signal. The Fourier transform of a cosine signal gives you 2 peaks. Now, let me ask you a question. When you have a signal that is cosine, right? And then when you do Fourier transform, do you get real number output, imaginary number output, or complex number output? Which one? How many of you say real number output? How many of you say imaginary number output? How many say complex number output? I want to shoot myself. It's a cosine wave. How do you do Fourier analysis again? You have a signal, you dot product with cosine, you dot product with sine, right? And then you use the result with dot product with cosine, you put it in the real part or imaginary part? Real part. The dot product with sine, you put it in the imaginary part, right? So if the signal is a cosine, when you dot product with sine, do you think you get any non-zero output? No, right? Sine and cosine dot product will always give you 0, right? Yeah? So you never have a imaginary output, understand? Okay? So when you have a cosine wave, and then you do Fourier analysis, your result will always real number, understand? Okay? I think I'm in trouble. Do you understand now? Okay, yeah? So it is real number, and you get 2 peaks. One is a positive frequency, one is a negative frequency. Okay, K0 is a frequency. Okay? And how to represent these 2 spikes? You use two impulses, right? There are 2 impulses, one at K0, one at minus K0. That's how you represent the 2 impulses. Is that okay? Okay, yeah? And remember, because we are discretized and all that, the whole thing repeat outside, understand? The whole thing repeat outside, but I'm just showing you one interval. Okay? Now, from cosine, then you go to sine. So when you have a signal that is sine wave, and then you do Fourier analysis, the output is real number, imaginary number, or complex number. How many say real number? How many say imaginary number? Okay, good. How many say complex number? Actually, those who say complex number also not wrong, because when you use FFT, they always give you complex number. It's just that the real part they give you 0, understand? Or some very small number. Okay, but it's practically 0, right? So conceptually, it is a imaginary number. If you have a sine wave, you do FFT, they'll give you imaginary number, but the FFT will still return you in complex number format. It's just that the other component, the real component is 0. Okay? So we read so So it's imaginary number, one is a positive j and another one is a negative j, understand? It's also at frequency k naught and minus k naught. And for positive j, we tend to represent it this way. Negative j, we tend to represent this way. But as you can see, this is quite arbitrary, right? Right? This is quite arbitrary because we are talking about imaginary axis now. Okay, but pictorially you write it this way, but you must know that it's also the sine wave, Fourier transform of the sine wave is also the two impulse functions. Okay, it's just that now both are imaginary. One is plus j, one is minus j. Okay. Okay. So you must know sine, cosine, Fourier transform. And impulse train, the train of impulses. Now listen. There's something that is not part of this course, but just want to share with you. There are only two types of signals in the world that after Fourier transform still give you the same type, understand? One type is what you're seeing here, impulse train. If you have a train of impulses in the time domain, in the frequency domain, the output is also another train of impulses, okay? Okay? The other signal that will not change its type after Fourier transform is the Gaussian function. If you have a Gaussian function, you do Fourier transform, it's still a Gaussian function in the Fourier domain, understand? Is that okay? These are the only two signals in the world, right? I didn't put it down in the slide because it's not so important for our class. But just some additional knowledge that you want to take note. Okay? Okay? Now the difference is, in fact, it's not just this train of impulses. It applies to any kind of scenario. When you stretch the axis in one domain, the other axis becomes compressed. Okay? So in other words, you have a train of impulses, right? You train of impulses, and then after the Fourier transform, you get another train of impulses, right? Now, this train of impulses is in the time domain. If the impulses happen very often, that means they are all crammed together, right? If they happen very often, they're crammed together. In this domain is also another train of impulses, but this train of impulses will be more spread out, understand? It's always like that. One domain crammed, the other domain is spread out. Okay? This is something that you have to remember. When one domain is crammed, the other domain is spread out. Okay? Any question? No question, I move on. The other thing is about a rectangular function. Rectangular function, I've drawn it this way, but if you increase this to be infinity and then shrink this, it becomes an impulse, right? Right? But let's look at the rectangular function. The Fourier transform of rectangular function is of this shape. There's a name for it. It's called sinc. S-I-N-C. Sinc function. Okay, S-I-N-C. Okay. You really don't have to memorize all these things. All I need from you is just to feel it and to know that the shape is like that. That's good enough for me. Okay. And there are normalized version and normalized version. I put it here just in case you are reading something and then people use a different definition, right? But by and large, the shape is still the same. Okay? So we look at some, are you okay so far? I move on. So we want to look look at some important Fourier transform properties. The first property, in fact, there are many properties. I just pick those that are useful to our concept form, right? The first one is a linearity property. Linearity property is like if Fourier transform of the addition of two signals is equal to Fourier transform of the individual signals add up together. That's what it means. Nothing special there, right? In fact, we have been assuming this in our treatment anyway, right? This linearity property. The second thing is something that is not familiar to you, but you have to know. The time shift in the time domain. When you do Fourier transform, you get the same signal, but it's phase shift. This is a phase shift. This is a phase shift. What is e to the minus j? This item is cosine, this item minus j sine, this item, right? You still remember the Euler's formula, right? So when you have a signal, you shift it by m, shift to the right by m, you get the same signal in the frequency domain, except that you have to multiply by this item. And this item here, okay, why do I say phase shift? What is the magnitude of e to the power minus j? What is the magnitude of e to the power j theta? What is the magnitude of e to the power j theta? Anyone? One, huh? Because e to the power j theta is cos theta plus j sine theta. The magnitude is equal to cos square plus sine square, right? Square root. So it's equal to what? Cosine square plus sine square equal to 1. I hope you all know, right? Right? So the Euler's formula, e to the power j theta equal to cos theta plus j sine theta, the magnitude is always 1. So the magnitude of the frequency results are not affected. It's only affected by this. And this is a phase component. That means it changes the phase. Okay? And what does it mean by changes the phase? I want you to go and think about it. Right? Sometimes to deal with problems like that, you just need to plug in numbers and see. Understand? Plug in numbers and see for yourself. Or use Jupyter Notebook to go and test it out. Similarly, when you shift in the frequency domain, the time domain becomes phase shift. You must ask me question. No question. No question. No question. No question, ask a question. Or maybe I should reserve it to exam. You know, over the years, we cannot repeat exam questions. Over the years, I find it very hard to set exam questions because run out of ideas. So actually, I have one question here, but since you don't ask, I don't want to ask. Maybe keep it for future exam questions. Really, no question to ask. Okay, never mind. This thing, if x is real, then x has this complex conjugate symmetry. I think we spoke about this last time, right? Right. So when a signal is real, right? Real signal is everywhere, right? You listen to music, you describe it. The music vibration in the air is some real numbers, right? The vibration is a real number, right? Real. Right. When the signal is real, the Fourier transform result exhibits complex conjugate symmetry. So what does it mean? It means this. When you have a signal, right? And then you do Fourier transform. So this is 0 hertz, right? Right. And say at position 2 here minus 2 here, you got some number, right? Right. What it means is, if the signal here is real, and most of the time we do real signals, right? If the output here is A plus JB, the frequency 2 is F plus J, frequency minus 2 here will be A minus JB. It will always be like that, understand? It's complex conjugate symmetry. Okay, that's what it means. You can draw it in your alright? Now, what is the magnitude of A plus JB? Equal to square root of A squared plus B squared, right? Right? What is the magnitude of A minus JB? It's also equal to square root of A squared plus B squared, right? Right? Okay? So when the signal is real, you'll find that when you plot the magnitude of the frequency spectrum, the frequency result, right? It's always symmetrical with respect to the zero frequency axis. I have uploaded tutorial number 3, and you will do tutorial 3, you can see for yourself. It's always symmetrical. The magnitude is symmetrical, the phase is not. The phase is like convex conjugate. Is that alright? And there's a proof of linearity. I'll leave it to you to go and figure out. This is actually quite simple to go through. I won't go through it here. You just see for yourself. Shift property also, I'll just leave it to you to see for yourself. The revision is here. And shift invariant here. Sometimes this is useful for, say, pattern recognition users. Right? Remember what I said just now? When you time shift the signal, when you time shift the signal, right? In the frequency domain, the magnitude is not going to change. It's just that the phase change only, right? So time shift in the time domain results in a phase shift in the frequency domain. Alright? And so let's say xn is your input, and then xk is the Fourier transform output. And then you shift xn. Let's say you shift xn, right? You shift on xn, then you get the same xk multiplied by a phase shift, right? I think we went through this just now. Time shift becomes a phase shift, right? But what's the effect of phase shift, right? The phase shift is if you do the magnitude on both sides. If you do the magnitude on both sides, the magnitude of the shifted signal in the frequency domain and the magnitude of the original signal in the frequency domain are the same, understand? Because the magnitude of this thing is 1. Magnitude of e to the minus j something is 1, right? So when you magnitude them, this thing goes away and you're left with xk. So the magnitude does not change when there's a time shift in signal. That's called the shift invariant property. Is that okay with everyone? So what's the application of shift invariant property in pattern recognition? You know, when I say, may the force be with you, right? May the force be with you. When play may the force be with you, then you start to record, right? You record. You are not going to be able to record the exactly here and here, right? And stop here, right? Your chances are you're going to record earlier and then cut off somewhere here, right? Yeah? So in other words, whatever you recorded must be a shifted version of what you intend to analyze, right? But it doesn't matter because the shifting is not going to change the frequency spectrum. You just attach phase shift to evenly, phase shift to evenly. And if you are using the magnitude, that means without a phase to do pattern recognition, then this thing doesn't, then this thing will work out because the magnitude doesn't change. I think I'm losing some of you. I'm losing some of you, right? Are you okay? Okay, yeah. So I think we'll stop here as far as the lecture is concerned today. So we have done this, and in the next lecture, so I hope you go back and practice in the tutorial, and practice in the tutorial, and in the next lecture, I want to teach you how to do frequency analysis for images. Right now we are only talking about sound, right? So when you do images, what do you mean by frequency in images? Right? It's different from the color notion of frequency, yeah? Right? When you see something in different color, it's different wavelength, so different frequency. It's not that kind of frequency. The frequency that I'm talking about is geometrical frequency. Okay? Then we will discuss that in our next lecture. Then after that, we will go on to a topic called convolution and sampling. Right? Any question? So remember I set up a mid-semester kind of informal feedback for you to let me know how are you progressing, right, in the Canvas under quiz, right? So please go and do it. And there will be a formal feedback later at the end of the course. But this technically semester one is more like one. Just let me know how are you progressing. Okay, thank you very much. Thank you. Oh yeah, by the way, your TA for Friday, I think she made a mistake. She told you tutorial is not compulsory, right? No, tutorial is compulsory.